Okay, that's great, guys. Once the truck pulls out, you can put all this over there by the plywood.
Okay, right on.
Okay.
Yeah,
Okay, I got you.
Thanks.
Hey.
Hey, dude.
No, not H-E-Y, like hey, dude. H-A-Y, like what's up with this hay delivery?
Oh, well, it's all part of a little project I'm working on.
What kind of project?
Well, you know we have the big math club holiday party happening later today.
Yeah.
I wanted to bring something fun to the party. Like, you're making Christmas cookies, right?
I am. My grandma's snickerdoodles.
And I wanted to make a Hanukkah surprise.
So what did you decide to do?
Do you maybe not know the word surprise?
Okay. I can wait.
Good. But don't worry, it won't be long. I'm expecting the last two parts of this project to show up any minute now. And there's one now.
Oh, hey, I'll get it. Hello.
Good day to you, brother.
What, good day. Can I help you?
Ah, yes. Noah warned me that you don't know about everything yet. I'm Sister Mary Mathematicus, at your service. Is Noah here so I can check in with him?
Just a moment, sister. Noah, if you'd given me a million-sided die and made me write a different idea on each face about who was going to be at the door, I don't think Math Nun would have made it on there.
Okay, hang on a second, dude. Sister Mary, if you would please head out to the backyard with all of the hay, someone will be with you shortly.
Gladly, brother. Thank you very kindly.
Okay, what's going on here, Noah? We've got all this hay and now a Catholic nun. How is she part of a Hanukkah surprise?
All in due time, Pete. All in due time. There's one more piece that's not here yet.
Oh, I can't wait.
Speak of the devil, that must be him.
Hi, I'm Jimmy Kimmel.
Hey, Jimmy. Thanks for coming. Would you mind following that nun out to the backyard?
No problem.
So now that you know the first three bits, do you think you can figure out my surprise?
Nope. I still have no idea what you're up to here.
Listen. Nun, Kimmel, hay, and...
Okay. Now I see what you're going for, despite the shoddy wordplay. But aren't you missing a shin?
And I have one right here. The shin bone of a duck-billed platypus. Happy Hanukkah! Get it?
Yeah, I get it. The 4 Hebrew letters on the sides of a dreidel. Nun, Gimel, Hey, and Shin, right?
Yes.
I thought so, but what's it all about?
Like I said, I wanted to make something for the party, so I decided to make a real live dreidel.
Okay, that sounds horrifying.
No, it's going to be really cool. Like one of those life-size chess games that kings and rich people play. Come on out back and I'll show you. Looking great, guys.
Whoa, that's a huge wooden cube. What is it, 8 feet per side?
Yeah. The 4 plywood faces are the sides of the dreidel. Then that 15-foot flagpole will go straight down through the center to be the part that you spin.
And what are the metal brackets on each face?
Whee!
Hey, careful with that part, guys. Don't make those brackets too tight. We don't want to hurt their wrists.
Don't tell me you're attaching people to all 4 sides of the dreidel.
Of course not. We've got the hay on one of the sides and this platypus shin for another.
I didn't think this could get any worse, and yet it just did.
My only problem is that Jimmy Kimmel has at least 40 pounds on Sister Mary, and they both weigh more than the hay and the shin. There's no way we can get a fair spin like that. Jimmy's side is much more likely to land face down since it's the heaviest.
Hey.
Oh, sorry, Jimmy. No offense.
No, I just meant that's a lot of hay.
Yeah, they were having a buy one, get one. But even with all that hay, that side is still going to be much lighter than the others.
Oh, I assumed that's what you were going for. You know, to emulate the real thing.
But a real dreidel has an equal chance of landing on any of the 4 sides.
Oh, does it now?
Doesn't it? Otherwise, it's not really a fair game.
Well, you're right about that. It's not a fair game, and not just because of uneven weight distribution.
What? I've been playing dreidel with my family every Hanukkah for as long as I can remember. Are you saying that countless pounds of chocolate coins may have been unfairly distributed?
Well, not on purpose, but that is kind of what I'm saying.
Okay, hold on. Let me get this platypus shin screwed into place and we can start playing with it so you can show me.
You know what? I think I'm going to pass on the spinning top of death.
Suit yourself. I have a few regular dreidels in my desk drawer that we can play with if you like that better.
Oh, I definitely do. So let's leave this contraption out here and head inside to investigate the relative fairness of the dreidel game.
Okay, but we only have Jimmy until 4:30.
I have a little dreidel, I made it out of clay, and when it's dry and ready, the dreidel I shall play.
Hey there, welcome everybody to another episode of the Math Club. Noah King, how are you doing? Season's greetings to you.
Season's greetings to you, Pete. I'm in the middle of a 3-week period between our Thanksgiving break from school and our winter break from school. And boy, do my students know that we are on a 3-week session. They are squirrely.
You get a lot of breaks that I don't get, my friend, and I am more than a little jealous, I'll be honest. I can't remember the last break. I guess I had 2 days off for Thanksgiving, and I will have about a week off around Christmas, but that's it.
Yeah, well, them's the breaks.
Bum, bum.
I will say that while I might get more breaks than you probably get a lot more cash than me. So it's a trade-off.
So what's new? What's shaking? How you been?
I've been pretty good. You know, the holidays are coming. I think a lot of our listeners probably remember the last time we did a holiday episode, we focused on the song, The 12 Days of Christmas. And we talked about how many gifts the singer receives from their true love. This year, I thought it would be fun, since my family and I are Jewish, to do an episode more geared around Hannukah.
Oh, I love that idea. That sounds super cool.
And incidentally, an interesting little fact, Hannukah this year starts at sundown on December 25th. So the first eve of Hannukah is on Christmas Day Eve.
Oh, that's actually really cool. Now, I know that Hanukkah starts on different days each year, and that's because it's on a lunar calendar, right?
That's right. Now, our secular calendar that we follow in the United States is based on Earth's orbit around the sun. It's 365 days. But the Hebrew calendar has 12 months that are all based on the cycles of the moon. And Hannukah falls on the 25th day of one of those months, which is called the month of Kislev.
When's it start?
On the 25th,
Of December?
Kislev,
Which is when exactly?
I will check.
Now, because we have 12 lunar months in the Hebrew calendar, it comes up to only 354 days, which is 11 days shorter than our secular year. So that's why Hannukah moves back 11 days every year. This year, Hannukah is starting on December 25th. Next year, it'll be starting on December 14th.
Okay, well, so that's interesting, because then that would mean December 3rd would be the next year. And then the year after that, it would be in November, right? Like even before Thanksgiving. But as far as I know, I can only remember Hanukkah taking place in December. So what's up with that?
Well, it actually can be anywhere from late November to late December. It does sometimes fall at the very end of November. But you're right, it doesn't just keep moving earlier and earlier in the secular year and end up sometimes in the middle of summer. And that's because, just like with the secular calendar, how it gets a little bit out of sync with Earth's orbit. I'm sure you know that the secular calendar has 365 days, but Earth's orbit is actually 365 and a quarter days. And so to adjust for that difference, every 4 years on our calendar, we add a February 29th, and that's a leap day, right? Well, the Hebrew calendar has something similar to keep it more in sync, but instead of adding a leap day, the Hebrew calendar gets a leap month that is periodically added to it. In fact, we add a leap month to the Hebrew calendar 7 times in every 19-year cycle. And those leap months do the same job that February 29th leap day does on our secular calendar of keeping things from getting too far out of sync with the natural world.
It's amazing that humans have figured out how to track any date ever on any kind of calendar, because it is so complicated. 7 times every 19 years, and then there's 365 days and a quarter. But even that's not exact. And that's why sometimes we don't have leap years in dates that are multiples of 100, but then we add them back in if the date is also a multiple of 400. And all I can say is that it is, I think, December 8th today, and I'm pretty sure it's a Sunday.
It is, but it's still amazing that we managed to schedule a time to record this episode and we both showed up at the same time.
Speaking of that, what are we going to focus on in this episode?
Well, I thought it would be fun to talk with our listeners today about the mathematics of the game of Dreidel, which is a common game that Jewish families tend to play at Hanukkah time. Have you ever played the Dreidel game?
I have, not a lot, but I definitely did. And, one of the things I remember most about it is those little chocolate coins that were wrapped in gold foil that you would use like when you anteed and if you won a round, that's what you got to keep. I'm very fond of those little chocolate coins.
I want to lock it all up in my pocket. It's my bar of chocolates. Give it to me now.
Yeah, those are actually called gelt. Gelt is the Yiddish word for money. And before we get too far into the math of the game, I think it might be a good idea if we talk for a minute about the rules. I suspect we might have at least one listener out there who's not familiar with the game. So let's talk for a minute about how the Dreidel game works. How does that sound?
Yeah, totally. So help us get into this. Let's imagine that you and 3 family members, there are 4 of you. You're going to play a round of Dreidel. How would it go?
Well, as we said in the opening sketch, the Dreidel is a top that the players spin. It has 4 sides that it can land on, and each of the 4 sides has a different Hebrew letter on them: Nun, Gimel, Hey, and Shin. And those 4 letters are the first letters of the 4 words Nes Gadol Hadar Shem, which is a Hebrew phrase that roughly translates to a great miracle happened there. So the way the game works is each player starts with a certain amount of gelt, a certain amount of coins. Let's say for the sake of our example that everyone has 8 coins in front of them. And to start, everybody sort of antes up. Everybody puts a coin into the center, into what's called the pot. And then each player kind of goes around the circle, taking a turn, spinning the Dreidel, spinning the top. And depending on which side it lands, you have a different action that you take. So let me tell you what those are. If the Dreidel lands on Nun, that means nothing happens. So Nun means nothing. You just pass the Dreidel and you don't put more coins into the pot, but you also don't take any coins out of the pot.
To the unfortunate player that spins a Nun, you get none. That's how I remember it. Like, none of that chocolate is now for you.
That's right. That's right. Now, the second thing that could happen is you might get a Gimel, not a Kimmel. It's a Gimel. And Gimel means that you get the whole pot. You take all the coins that are currently in the pot and you win them and then start a new round.
All right. So Gimel is the sweet spin. That's the one you really hope to land on.
Absolutely. You get everything for a Gimel. The third option that you might land on is the letter Hey. If you land on Hey, you win half of the pot.
I got to tell you, Noah, that's not half bad. But what do you do if there are, let's say, 5 coins in the pot and you spin a Hey? How do you get half?
Well, what you would do is you would take half the pot rounded up. So if there were 5 coins in the pot, you would take 2.5, rounded up to the next whole number is 3. So you would take 3 coins in that case.
That really isn't half bad. That's a lot better. Cool. Okay. And now tell us about Shin.
Right. And if you land on Shin, that's actually the most unlucky spin you could have, because if you land on Shin, you have to take one of your coins and put it into the pot. Once you spin the Dreidel and take the corresponding action, you pass the Dreidel to the next person and play continues around the circle. And you usually go until somebody has won all the coins and they're the big winner.
Okay, so I think that's a good explanation of how the game works. And I think there's a lot of interesting probability involved. So it would be kind of fun to dive into this.
Yeah, and I'm particularly intrigued by something you said at the end of our opening sketch. You said that Dreidel is not a fair game, which would imply to me that not everybody has the same chance of winning.
Well, who says life is fair? Where is that written? Life isn't always fair.
And you also indicated that this wasn't simply because the Dreidel might be off balance, but that there was a more mathematical reason that it's not fair.
Yeah, and I think this is a really surprising result, because if you had asked me a few weeks ago, do I think Dreidel's a fair game? I would have said, yeah, it's a game of luck. So there will be winners and losers, but I didn't really intuit that there was something unfair about it until I actually started looking at the mathematics of it.
All right. And what did you find when you did that?
Well, so it turns out that back in 1976, there was a paper published in the American Mathematical Monthly entitled An Ancient Unfair Game. This was published by a mathematician named Robert Feinerman, and we'll put a link to this paper in the show notes so that listeners can go check it out for themselves. But in this paper, Feinerman basically gives an analysis of the probabilities, how they accumulate over time, and demonstrates very conclusively that player one has a distinct advantage over all other players. And then player two has a distinct advantage over all players that come after the second spot. And this persists so on until you get to the last player, who unfortunately has the least likelihood of coming out ahead.
So let me get this straight. Even a completely fair dreidel, which has exactly a 25% chance of landing on any of its four sides, is not going to result in all four players having an equal chance of winning.
That's right. And this seems particularly surprising because you think, well, okay, so player one starts off from sort of the reset position, right? Everybody's got their coins in the middle and the spinning starts. And then somebody will get a gimmel that will cause the pot to be reset. And you would think that whoever was about to spin effectively becomes the new first player. And so therefore, they should enjoy whatever benefits player one had received, and so on down the line. It turns out that isn't the case. Player one still, nonetheless, has this abiding, persistent advantage throughout the entirety of the gameplay.
Okay, well, I'm super intrigued. Can you walk us through the math and kind of explain as we go how this result makes sense?
Yes. And I think what we should do to start out with is to make a few simplifying assumptions, because there are some peculiar rules about Dreidel, which might be difficult to model mathematically, at least initially. And what I'm thinking here in particular is what to do when a hay shows up.
Okay, and that's the one where you take half the pot rounded up.
Yeah. And so it's that rounding up in the case when you have an odd number of coins in the pot versus not rounding up when you have an even number, that I think we want to simplify by simply saying, let's assume that we can take exactly half of the pot. So we'll allow fractional coins, and we will just assume that every hay splits the pot exactly in half.
Okay, and that's going to make the math a little bit easier to work with. That's why we're doing that.
Yeah, it'll make it significantly easier. And we'll circle back and address what would happen if you didn't do that. We can talk about that too. But there is another benefit to making this assumption about hay. And that's because in ordinary dreidel, if there's only one coin in the pot and somebody spins hay, then it is effectively the same thing as a gimmel, because now the pot is empty and everybody starts over. So the fact that hay can every once in a while act like gimmel makes the analysis even more difficult.
Okay, so for our purposes, let's just say that a hay means take exactly half the pot, even if that's half of a coin or a quarter of a coin or what have you. So there's never really a need to clean out the whole pot on a hay like you would on a gimmel.
Yeah, and that's really going to be helpful because, as we'll see in a moment here, the gimmels are pretty important and they play a rather significant role in the unfolding analysis of why player one has this advantage.
Okay, so we're going to allow for that assumption. But like you said, at the end, let's circle back and see how restoring the actual rule will affect our result.
Sure. And I think to get started here with our analysis, I think we can both agree that the gimmel is a pretty important spin in the context of dreidel because of its property that it resets the pot. So as a first step in our analysis, we're going to follow Feinerman's lead here and imagine that we are spinning the dreidel and not getting any gimmels. So let's pretend that gimmels aren't happening. And we want to analyze what happens to the pot over time as successive spins come in, but none of them are gimmels. Let's start with some amount in the pot, and let's call that quantity A for amount. So we've got some number of coins in there, some quantity that we're calling A. Now, my question for you is, what can we expect to be in the pot after a single spin of the dreidel, given that Gimel isn't an option?
All right. Well, it seems like I would have a 1/3 chance of getting a nun, in which case the pot doesn't change at all. So it's still going to have A in it. Is that what you mean?
That's exactly what I mean.
All right. So that's 1/3. There's another 1/3 chance that I'm going to get hay, which means I take half the pot, which means the pot now has A/2 left in it. And finally, there's a 1/3 chance that I will get shin, meaning I have to put a coin into the pot. So now it's going to have A+1.
Yeah, exactly. And this is how expectation works in the world of probability. You multiply the probability times the quantity. So the probability of each of these spins is 1/3, and you just identified exactly what the quantities are. There could still be A, there could be A/2, or there could be A+1. And so when we gather all of this together, we end up with 1/3 times 5/2 A plus 1. That's the expected amount that will be in the pot after we spin the dreidel a single time.
All right, got it. And I just want to say I can see already how the way that we're treating hay is simpler because we can just say when you land on hay, the pot becomes A/2 and not have to worry about those extra remaining ones if there's an odd number in the pot.
Yeah, so there's already a payoff here for us. Now, it turns out that this expression that I rattled off, 1/3 times 5/2 A plus 1, although completely correct, is not the best form to carry out our analysis. And so I'm going to do a little bit of algebra. I won't go into the details here, but this can be rewritten in this form. 2 plus 5/6 times the quantity A minus 2.
Good form, Peter.
Okay, sure, but why is that easier to work with?
Well, it turns out what we want to do is repeat this process, is we want to ask, well, okay, what if I did another spin? What could I expect to find in the pot? And then a spin after that, and then a spin after that. Well, this form that we just wrote this in, 2 plus 5/6 times the quantity A minus 2, is very well suited for this repetition that we want to carry out. Because ultimately, we'd like to know over time, with many, many spins under our belt, what can we expect to find in the pot? This is the version of the formula that will really help us see that.
Okay, and before we go on to the second spin, I just want to pause for a second and use a real number and figure out if the pot starts with 4 coins in the middle, and then we say, okay, that means A = 4. What would your expression evaluate to if we started with 4?
That's a great and totally fair question. So in that case, A minus 2 becomes 4 minus 2, or 2. And multiplying that by 5/6 gives me 10/6, right? Which I can rewrite as 1 2/3. I have that 2 out in front, so I end up with 3 2/3.
All right, so what we're saying basically is the first player who's spinning has a pot of 4 that they are hoping to win. And the second player has an expected pot that they're inheriting after the first player's spin of only 3 2/3. So expected value tells us that player 2 has a slightly smaller pot that they now have a chance of winning than player 1 did.
Exactly. And that is essentially what this 5/6 multiplier is telling us. Each time you multiply some quantity times 5/6, well, it's going to get smaller.
Okay, but I notice it's not 5/6 times the whole pot. It's just 5/6 times the pot minus 2. What's that about?
Yeah, that's an interesting feature here. And here's a way I want listeners to think about this. So imagine that you've got the pot laid out in front of you, a bunch of coins on the table. So take 2 of them and just push them off to the side, move them, say, off to the left. And what you now have directly in front of you is A minus 2. You started with A, you put 2 of them off to the side, and now you have A minus 2. It's that slightly smaller amount, A minus 2, that you want to multiply times 5/6.
All right, but then if I'm understanding correctly, after you multiply it by 5/6, then you slide those 2 back in and lump them back in with the result. Is that right?
That is right. And so that's why the reduction from 4 down to 3 2/3 wasn't a little more substantial, right? If you simply multiplied 4 times 5/6, then you would have gotten a smaller number.
Oh, so if you had multiplied the whole pot of 4 by 5/6, 4 times 5/6 is 26, which is 3 and 2/6, 3 and 1/3, which is a little bit smaller than our actual answer of 3 and 2/3.
Exactly. And that's just a curiosity of how Dreidel works, right? There is this scaling effect of 5/6, but it doesn't apply to the entirety of the pot. You have to set 2 aside, then scale down, and then you can bring the 2 back.
Okay, and then when player 2 starts with a potential pot of 3 and 2/3, and they do their turn, if we wanted to then calculate the expected value of the pot going to player 3, we would do the same thing. We would take 3 and 2/3, we would set 2 aside, so we have 1 and 2/3. We would multiply that by 5/6, and then add the 2 back. What does that leave us for player 3's expected pot?
Well, it turns out I've already calculated that answer, and it leaves 3 and 7/18 in the pot, which is in fact less than 3 and 2/3.
Okay, so I'm starting to see where this result comes from that says that each player has a slightly higher chance of winning more coins than the players that come after them, because each subsequent player's expected pot that they're inheriting from the player before them is a little bit smaller. So even if we put Gimmels back in and they were to roll a Gimmel, there's a likely smaller pot left for them.
That's exactly what this result is telling us. Now, let me just circle back to something you said a moment ago. When we repeat this process of asking with each new spin, what is the expected amount? The formula that captures what you described in that process is the following. So if I spin the dreidel some number of times, let's say that that number is called K, then the answer is 2 plus 5/6 raised to the kth power times the quantity A minus 2. So I'm not expecting listeners to be following all of this along in real time. I did want to give the formula in case folks do want to go back and sort of dwell on it. But in each case, what you can imagine happening is you set 2 coins aside, then you multiply what's left by 5/6, and then 5/6 again, and then 5/6 again, however many spins you're interested in. And then you bring the 2 back. And that is the expected quantity the pot will have after some number of spins of the dreidel.
That's really interesting. And I just want to pause and point out something. We're not saying that player 1 is always going to win. We're saying that when you compute the likelihood using the expected value or the expected payout, player 1 over several games has a clear advantage mathematically. But just like whenever you're flipping a coin or rolling a die or spinning a dreidel, different things can happen that might say that player 2 actually ends up winning this round. They're not the most likely to win this round, but they could.
Oh, yeah, it's very reasonable. Player 1 might spin a shin, and now they have to put a coin into the pot. And now there are 5 coins in the pot, although our calculation said that we should expect there to be 3 and 2/3. So clearly, as you say, we're not giving a definitive answer to what will be in the pot, but on average, what is the likely quantity? Let's say we repeat this experiment 10,000 times and then take the average of what is in the pot after the first spin. It's going to be pretty close to 3 and 2/3.
Gotcha.
So there's one other thing that's at least worth mentioning here, which is if we think about this formula that tells us how much I would expect to find in the pot after some number of spins, and I let that number of spins go to infinity and ask for the limit, listeners can go back and check that the limit of those expectations is 2. So if Gimmels are not present in the game, we would expect over time the pot to decrease from its starting quantity, say of 4, down to a stable value of 2. So I think that in and of itself is interesting. It does tell us that in this formulation, in this simplified setting, we're not going to expect the pot ever to disappear. We're going to expect always for there to be 2 and just a little bit more.
It takes 2, baby, me and you.
Okay, now that makes sense. I mean, I never took calculus, so I don't know that much about limits or how to calculate them, but this one just makes sense to me. We're always setting those 2 coins aside first and then bringing them back in at the end. So no matter how small that fraction gets from multiplying 5/6 by itself over and over, we can't ever end up with fewer than 2 coins in the pot.
Yep, totally. You got it.
Okay. And then what happens now if we allow for the possibility of gimmels again? How does that affect things?
Good question. And that's exactly the next step in the analysis. Now, the details get a little involved. And so I'm going to direct interested listeners to go look at Feinerman's original paper. But essentially, his analysis unfolds like this. So we know what happens now to the pot if no gimmels are rolled. So what we want to think about is, all right, suppose we've been playing the game for some number of rolls. Let's say that we're on spin number N. Maybe N is 17, maybe N is 32. We're just at some point in the game. And what we want to do is ask, when was the last gimmel observed? Because gimmels have this resetting quality, right? The pot gets cleared out and then everybody antes in again. So there's this reset that happens. We want to ask, when did the last gimmel happen?
Let's say we just had a gimmel and then the next player spins one again.
So if we just got a gimmel, then that means that the current player will have 4 coins in the pot. Again, we're assuming that we've got 4 people sitting at the table playing. And so now, given that gimmels are an option again, what can that player expect the payoff to be at this point?
Well, they have a 1/4 chance of rolling a nun, which would mean that their payout is nothing. They would have a 1/4 chance of spinning a gimmel, which would mean their payout would be 4. They have a 1/4 chance of rolling a hay, which would mean their payout is 2, because they would get half the pot. And then they have a 1/4 chance of rolling a shin, which is kind of a reverse payout because they have to put one in. So in that case, I guess we would say their payout is -1, right?
Yeah, if they spin a shin, their so-called payoff would be -1.
So to figure out their expected payout, we would multiply each of those by 1/4 and add them all together.
That's right. And if you do that, you end up with 5/4. So after a gimmel, you can expect the payoff to be 5/4.
Okay, that makes sense.
Now, of course, that answer is dependent on the fact that we started with 4 coins in the pot. And that's because we had assumed that there are 4 players who are playing. If instead you had 6 or 7 or 10 people playing, your answer is going to change slightly because you don't start with 4 coins in the pot. You start with however many players you have.
Right.
But scoping this down to 4 players, the expected payout would be 5/4. So then you say, all right, but it's not always the case that the previous round was a gimmel. It could be the case that the most recent gimmel happened 2 rounds ago. And if the previous gimmel happened 2 spins ago, how can we understand what the current player can expect to win on their spin?
Well, then I assume that's where we would pull in that result that we were talking about a few minutes ago, where we said, what is the expected value of the pot after a spin that isn't a gimmel? And we said at that point, the pot is no longer 4, that the expected value is 3 2/3.
That's right. And so the player has those same 4 probabilistic outcomes, but the pot is slightly smaller. It's only 3 2/3. And then we continue with this analysis and ask, well, what if the last gimmel had happened 3 rounds ago? Well, we do the same thing, but the pot will be slightly smaller. We know that we can expect it to be 3 7/18. So we apply the probabilities to that. And we go all the way back to the scenario in which there actually haven't been any gimmels yet. And then we apply the same 1/4 probability analysis to get a result in that case.
And so each subsequent player has a potentially smaller pot that we're applying this probability algorithm to.
That's right. And, one thing we have to remember is that the question of when was the last time we saw a gimmel is itself a probabilistic question. Because if we say we haven't seen a gimmel for 3 spins, then we have to ask, well, what is the probability of having seen a gimmel 3 spins ago, but then no gimmel, and now it's our turn. So all of this stuff gets a little bit involved, but our fearless author here, Robert Feinerman, carries out the analysis and gives us a final formula that encapsulates the expected payoff for each of the players in the game.
All right. And what does Feinerman's formula tell us?
Well, essentially, his formula also involves this scaling multiple. Now, it's not 5/6. In this case, it turns out to be 5/8. But again, you'll notice that 5/8 is less than 1. Anytime we take a number that's less than 1 and successively multiply it by itself, we get smaller and smaller quantities. So what his formula ultimately shows is that the player who spins first has the maximal expected payoff. And with each successive spin, the payoff gets smaller and smaller and smaller for the entirety of the game.
Hey, let's get small.
Irregardless of when the gimmels get spun and who spins them.
Exactly. And that's what's so surprising about this. Intuitively, you might think, well, sure, the pot is getting smaller and then there's a gimmel and it resets everything. But what Feinerman's formula shows us is that, in fact, that doesn't matter. That resetting quality of the gimmel isn't enough to overcome the advantage of having started the game earlier in the rotation.
Now, that's really fascinating to me. It seems totally intuitive that whoever goes next after a gimmel would inherit all of the advantages that the formula gives to player one. Like you just mentioned that a gimmel kind of resets the pot, and it seems like it should also reset who has the advantage now. But why doesn't that happen?
Yeah, I think it's a little mind bending to sort through some of this stuff, but here's one way to think about your question. When a gimmel occurs at some point in the game, say on round 10, well, players have already received payoffs for the previous 9 spins. And during those 9 spins, player one was expected, on average, to receive a higher sum than player two. And player two was expected to receive a higher sum than player three, and so on. So the players don't have the same number of coins they started with. If you were thinking about a reset at this point, well, whoever goes next, they likely have fewer coins to play with. So it's definitely not a full reset, because that would imply that every player has the same number of coins available for play.
Oh, okay, I get it now. Like if everyone had 8 coins to begin with, then after the very first ante, each of them would have 7 coins. But by the time they get to the 10th spin, maybe player 2 only has 5 coins left, while player 1 has 12 at this point. And I don't really think player 2 is going to feel like things have been totally reset.
Right. They wouldn't feel that way.
But now I have a question that we said we were going to come back to. And what I want to know is this. All of the math that we've been talking about has been under the assumption that we're just going to split the pot in half if somebody spins a hay. We kind of put to the side temporarily the rule of half rounded up. So if we were to now go back and say, how does this all play out in reality when we do take half rounded up for a hay? Does player one still have this distinct advantage?
Well, I did some modeling on the computer. I wrote some code to simulate both this model that Feinerman presents. In other words, gameplay is based on this modified rule for hay, where we just simply cut the quantity in half, and then we let the game play until some stopping point. I also modeled the situation of the actual Dreidel game, where hay means half rounded up in the case of an odd number of coins, and looked at those comparisons against, let's say, 10,000 or 100,000 rounds of play to see what are the expected outcomes for each of the players.
All right. And what did you find?
Well, first of all, I found that this mathematical model with this modified hay rule is remarkably good at modeling exactly what happens over time in real gameplay. And in both cases, the simulation is clear. Player one has a distinct advantage over player two. Player two has a distinct advantage over player three, and so on, regardless of how many players are involved.
Wow. So even when we put the hay rule back in the way it's supposed to be, these advantages persist.
Yes, that's right. So suppose that we play the real Dreidel game. We have 4 players, and we're going to play this game 10,000 times. And each game will run until one player has accumulated all of the coins in the pot. And at that point, the game is over, and then we'll mark down which player was the winner, and then we'll play again. And we'll do that for 10,000 times.
All right. And when you did that in your simulation, what were the results?
Well, we would expect for a fair game that every player ought to win about 2,500 times, right? 10,000 trials, 4 players, 2,500 outcomes they should win. Well, it turns out in this particular run, player one wins 2,670 times.
So more than the 2,500 that they would win if it were completely fair, but not so much more to make this advantage super blatant and obvious.
Right. And in fact, for player two, they only win 2,546 times. Player three wins slightly less than their expected amount with 2,461. And then finally, player four in this trial only won 2,323 trials.
So I think what this is showing me is why it was possible for my cousins and sister and I to play Dreidel every Hanukkah growing up and never even noticed that there was a slight bias towards player one to win.
Yeah, exactly. First of all, these outcomes are, I'm only seeing them if I run this game 10,000 times. I'm going to guess you have played far fewer than 10,000 rounds of Dreidel in your life.
I played Dreidel every Hanukkah growing up. So let's say 15 years worth of Dreidel games. And we probably would play a few games every year. So I probably only played Dreidel about, 50 times, maybe 60 or 70 tops. Not enough to make this bias truly noticeable.
Well, let's actually run this up to 100. Let's just round up to 100. When you played a typical game, how many of you were there?
Well, it would be myself and my sister, my cousin Dave, my cousins Mike and Stacy. So usually about 5 of us, I would say.
All right, let's suppose that 5 people are playing Dreidel and we're going to do 100 games. All right. Now, remember, the fewer games you play, the more likely you are to see the probabilities swinging around more. You don't see the stable behavior until you play many, many trials. But let's see what the simulation tells us.
So what you're basically simulating here is my real life experience with playing Dreidel with my 4 cousins and me about 100 times over the course of our childhoods.
That's right. And this is telling me on this most recent run, player one only won 21 times, only one more time than the expectation. Player two wins 22 times. Player three won 23 times. Player four won 20 times. And coming up last, I don't know if this was your sister Marnie or not, but they only won 14 times.
You are disappointment, sister.
Well, this is interesting because player 3 won more games than player 2, who won more games than player 1, which is the opposite of what the odds predicted.
Right. And that's because we only ran 100 trials. Let's see what happens if I run 10,000 trials instead. So, okay. All right. In this case, the results align much better with the prediction. Player one wins 2,205 times. Player two, 2,057 times. Player three, 2,015 times. Player four wins 1,937 times. And player five brings up the rear with just 1,786 wins.
Okay, that sounds more like what we were expecting. So we see how the results change when we add more trials. What if we add more players?
Yeah. Now, what's very interesting is if I were to imagine a very large number of players playing the game, something interesting happens. So let's take 32 players. Let's suppose you and your 31 cousins have gotten together and you're going to play 100,000 rounds of Dreidel. And
all right, I'm going to need a lot of gelt.
I would like a lot of gelt, and I would just keep it. I wouldn't even play. I would just eat it. All right, so I'm running the simulation now. It's a little bit lengthy because 32 players playing 100,000 rounds is taking some time, but let's see what it comes up with. Here is the result. With 32 players playing 100,000 rounds of the game, player one wins 5,891 times, and player 32 only wins 1,102 times. That is a huge difference.
Wow. So player 1 is close to 5 times more likely to win than player 32.
Exactly. And as you look down the line from player 1 to player 2 to player 3, it is a steady decrease. Everybody, as you move down the line, wins fewer and fewer times until you get all the way down to the bottom and you find that Well, I think this might be Marnie again here, bringing up the rear. She only won 1,102 times.
You are so disappointing on so many levels.
Sorry, Marnie. Well, this is a really interesting result. It is incredibly counterintuitive to the way I thought Dreidel worked. And when you first said something at the top of this episode about how this wasn't a fair game, I found that to be an incredibly puzzling thing to say.
As puzzling as it may have been, I think the mathematics gave us just the right amount of insight to sort of cut through the mystery and see what was really going on.
It did. It did. And speaking of puzzling, I'm reminded of the fact that at the end of our last episode, we left our listeners with a challenging puzzle for them to try to solve. I said that if you take all of the unique digits from 0 to 9 and rearrange them into as many different 10-digit numbers as you possibly can, there are 3,265,920 different 10-digit numbers that each use all 10 of the digits from 0 to 9. And the question was, how many of those 3.2 million numbers are prime?
Well, did anybody write in with an answer?
We actually received answers from several people. The first person to call in with the right answer was Neil Epstein. And why don't we take a listen here to his answer?
Hi, this is Neil Epstein, and the answer to your puzzle is that none of those numbers are prime because every one of them is a multiple of 9 because those digits add up to 45, which is a multiple of 9.
Very cool, Neil. You nailed it. That's exactly right. Way to go.
Yeah, nicely done, Neil. I actually think your approach on this might have been similar to mine when I first tried to solve it.
Oh, yeah? What was your approach?
Well, my initial thought was that the answer kind of had to be that none of these numbers were prime, because if there was some non-zero amount of primes here, I wouldn't know how to start to figure out what they were.
Oh, okay. So because you wouldn't be able to figure that out, the answer had to be 0. Is that right?
Yeah, exactly. So I started eliminating options like no primes are even, so it couldn't end in 2, 4, 6, 8, or 0. And it couldn't be a multiple of 5, so it couldn't end in 5 either.
Actually, that's a pretty good way to start looking at it.
Thanks. But I think, like Neil, the aha moment was when I remembered that easy trick for finding out if a number is a multiple of 3. You add up the digits and see if the sum is a multiple of 3. And then before I even added them up, I kind of suspected that I'd found the answer.
Yeah, that was really clever of you, Neil. And to a lesser extent of you, Noah.
Hey,
I'm totally kidding. Great job to everyone who figured out that the answer to this puzzle is 0.
Yeah. And I also want to point out 2 other submissions that we received came from a pair of listeners who are brothers, Stephen Corin and Kevin Corin. Both wrote in with the right answer. And I'm mentioning it because just in the spirit of sibling rivalry, as a big brother myself, I know how much it must have grated Kevin that his brother Stephen wrote in with the right answer one day before Kevin did.
You ought to spend a little more time dealing with yourself, a little less time worrying about what your brother does.
Sorry, Kevin.
Sorry, man.
All right, Pete. I love the analysis of the Dreidel game that we were able to do, and I want to thank you for walking us through it.
You're welcome. It was my pleasure. And I would like to say to all of our listeners who celebrate Hannukah, a very happy Hannukah to you and your family and your friends. And to everyone else out in our audience, I hope you have just the best winter holiday season. Sending you all the best wishes for the new year from the 2 of us to all of you. Thanks for joining us, and we'll see you next year.
Yeah. Happy holidays, everybody. Hey, Pete, after we stop recording, you want to play a little game of Dreidel?
Oh, I ate all the gelt. Sorry. Do you have some I could borrow?
I do have some gelt that you can borrow, but I get to go first. We'll figure it out off the air.
See ya, everybody.
Bye, Math Club.